Hi, I'm Max, and today we'll explore how a unique kind of geometry can be used to better understand how we can utilize the networks all around us. Networks show up everywhere in our lives. Think about how you get to school or work. Maybe you use the network of public transport. Did you think about it? If so, you use the intricate network of neurons that makes up your brain, and I surely hope to engage that with the rest of the video. And of course, without the internet, the world's global communications network, you wouldn't be able to watch this video at all. Because networks are so important, we study them in order to unlock ways to make using them as efficient as possible. But we do not study each network individually. That would be rather tedious, and whatever we learn on one network may not translate to another. Instead, we sort networks into groups based on shared properties. Then we study the groups, and whenever we encounter a new network, we figure out to which group it belongs and can make use of everything we learned about the group before. One such group that contains networks from a variety of areas are what we call complex networks. Complex networks are mainly characterized by two key features. The first is heterogeneity. It captures that there are a few nodes or vertices in the graph, like the blue one, that have a high degree, meaning they have a lot of edges to other nodes, while most nodes, like the red ones, have a small degree. Think of it like in a social network, where there are a couple of celebrities while most people have only few connections. Mathematically speaking, if we plot the degrees of the vertices on one axis and the fraction of vertices that have this degree on the other, then we tend to see a curve like this, which is called a power law degree distribution. The second property that is typically associated with complex networks is called clustering. It states that if we consider a node like the yellow one and look at the neighbors of that node, then we find a lot of edges among those neighbors, meaning together with the yellow node, they form lots of triangles. So now you know what we are studying, but I haven't told you yet how we study such networks. To this end, we use so-called generative graph models, which are mechanisms that can be used to create networks. A simple one may take a set of vertices, and for each pair of them, like the two blue ones, we flip a coin to decide whether there should be an edge between them. Some pairs will connect, while others, like these two, might not. If we repeat that for all vertex pairs, we end up with some graph. This model is simple, which is great for mathematical analyses. But it's not very realistic. So whatever we get out of an analysis may not actually apply to the networks we encounter in the real world. And by realistic, I mean two things. On the one hand, it refers to structural properties. So, do the produced graphs feature the characteristics we see in real-world networks, like the heterogeneity and clustering? On the other hand, it also refers to algorithmic properties, meaning, do algorithms perform on the generated graphs as they do on the networks we encounter in the real world? In our studies, we focused on this second part and wanted to figure out whether my favorite generative graph model, which are hyperbolic random graphs, can help explain how algorithms perform on real-world networks. Before we dive into that though, let's take a quick detour into the fundamentals of hyperbolic geometry. One of the most fundamental differences between hyperbolic geometry and the Euclidean geometry we are typically familiar with is how space expands. In Euclidean geometry, space expands polynomially, but in hyperbolic geometry, the expansion is exponential. In a sense, there is more space in the hyperbolic plane. So when I try to project that onto the Euclidean canvas of this video, the space gets distorted. In the blue region, space looks somewhat Euclidean, but as we move into the red regions, farther from the center of projection, the representation of space gets denser and denser. In other words, the red regions contain more space than there appears to be. Here's an example. The circle is centered at the white dot in the center of our projection. Since space expands equally fast in all directions, it appears just like a Euclidean circle. And if we divide the interior of the circle into two equal halves, there is again no surprise here. But watch what happens when we move the circle towards the red region. Our circle gets squished into this teardrop shape, and while it may not look like it anymore, all points on the circle still have equal distance to the white center point, and the shaded region still makes up half of the interior of the circle. It looks smaller to us, but there's more space in the red regions than there appears to be. And so indeed, the shaded region in the circle and the rest of its interior have equal area. And there's more to see here. The blue points were at the top and the bottom of the circle before, and if we wanted to walk from the top one to the bottom one on the shortest possible path, we would still have to go through the center of the circle like this. What we would typically believe to be the shortest path between them goes through a lot of space further in the red, meaning this path is much longer than it looks. And we can see that if we move our center of projection back to the circle center. So basically, what I want you to remember here is that there's much more space in the red regions than there appears to be. By now you may be wondering, how can we utilize this fancy geometry as the basis for our generative graph model? Well, Kryukov et al., who introduced the model in 2010, proposed the following mechanism. We take a disk, like this one, and distribute the nodes of our graph uniformly at random in it. At first this may not look like a uniform distribution, since there are more nodes closer to the boundary of the disk than there are near the center. But as we have just seen, there is more space in the red region, so in a uniform distribution we should also expect more vertices there. So now that we have the nodes, how do we get the edges? Well, for that, let's look at a specific node. We take a disk that has the same size as the one we distributed the nodes in, but we center it at the blue node. Now we find all other nodes that lie in that disk and we draw an edge to each of them. When we do this for all nodes, we end up with a nice graph. Unfortunately, all that distortion makes it hard to grasp the structure of the resulting network, which is why I'll draw the edges as straight lines instead. Keep in mind though that they are typically longer than they look. Now just by looking at the graph, we can immediately see its nice structural properties. We have already seen that the neighborhood disk of a node close to the boundary covers only a small portion of the disk we distributed the nodes in. So as a result, the node has a small degree. In fact, the majority of the vertices are closer to the boundary, so most vertices in the graph have a small degree. On the other hand, for the few nodes that are closer to the center, the neighborhood disk of the very same size covers a much larger portion of the disk, and so these nodes have a high degree, and we end up with the desired power law degree distribution. Moreover, the nodes that lie within a neighborhood disk of a node are typically also close to each other, meaning we find lots of edges among these nodes, and together with the blue node, they form lots of triangles. So we have just seen that hyperbolic random graphs nicely mimic real-world networks in terms of degree distribution and clustering. They also have a small diameter, another feature seen in practice, and further structural properties like component structure have been studied extensively. And there have also been some algorithmic insights about hyperbolic random graphs. We know how to generate them efficiently and how to find the maximum clique within them. There are some algorithmic results based on bounds on their tree width, and they can be compressed efficiently. However, from an algorithmic perspective, what's been mainly missing so far are the ties to real-world networks. Can we learn anything about how algorithms perform in practice by studying hyperbolic random graphs? During my studies, we have performed a series of analyses to explain empirical observations theoretically using the hyperbolic random graph model. This started with an analysis explaining why the bidirectional breadth-first search for computing shortest paths performs much better in practice than one would expect in theory. Closely related to path search, we developed a greedy routing scheme with some nice performance guarantees in networks with underlying hyperbolic geometry, and observed that it also works very well on real-world networks. But my favorite part is what we discovered when investigating the vertex cover problem on hyperbolic random graphs. So let me share some of our findings. First, let me explain what the vertex cover problem is. We are given a graph like this one, and we say that a given node covers its incident edges. For example, the blue node covers the blue edges. A vertex cover then is just a set of nodes that together cover all edges. Or think of it this way. If you remove a vertex cover from the graph, all edges are removed with it, meaning all remaining nodes are isolated. Vertex cover is one of the fundamental NP-complete graph problems, which means that it has been studied extensively, yet we do not know an algorithm that solves it efficiently. However, it has been observed that so-called reduction rules work exceptionally well on real-world graphs, allowing us to solve instances with millions of nodes in a few seconds, even if the solution itself is as huge. In essence, reduction rules help us pick off the low-hanging fruits when deciding whether a node should be part of the vertex cover. One example is the dominance reduction rule, which works as follows. if we have a node in our graph, like the blue one, and we look at its neighborhood, and among the neighbors we find a node, like the yellow one, whose neighborhood is completely contained in the first one, meaning all neighbors of the yellow node are also neighbors of the blue one, then we say that the blue node dominates the yellow one. And the reduction rule states that it is never wrong to add a dominant node to the vertex cover. So we just add it to the cover and remove all its incident edges from the graph, since they are covered now anyways. As a result, we have reduced the graph to a smaller version for which it is slightly easier to find a solution. Now, as I said, this reduction rule works really well on real-world networks. So let's check what it does on hyperbolic random graphs. Recall how we constructed a hyperbolic random graph. We distribute nodes in such a disk, and all neighbors of a node are contained in its neighborhood disk. Now take this yellow node. Its neighborhood region is entirely contained in the blue node's region. This means that the yellow node and all its neighbors are adjacent to the blue one. So the blue node dominates and can be safely added to the vertex cover. This remains true if we move the yellow node closer to the boundary of the disk. And in fact, we can use the geometry to trace the region containing the nodes that are all dominated by the blue node. We can move the yellow node like this, but at some point we cannot move it any further. If we did move further, there would be a region that could contain neighbors of the yellow node that are no longer neighbors of the blue node, in which case blue would no longer dominate. But if we ensure that the yellow region is always contained in the blue one, at least inside the white disk we distributed the nodes in, then we end up with an almost triangular shape. Any node within this region is dominated by the blue node. So if at least one node of our random graph ends up in this region, we can safely add the blue node to the vertex cover. Well, as it turns out in this case, the blue node dominates a lot of vertices. And in fact, the probability is high that all nodes that are not too close to the boundary of the disk dominate and can therefore be added to the cover. In particular, this gets rid of the high degree vertices. For the remaining graph, we were able to show that it has small path width by constructing a circular arc supergraph with a small clique number. This allowed us to prove that the vertex cover problem, that is NP-complete in general, can be solved in polynomial time on hyperbolic random graphs with high probability. This was already a really nice insight and a good step towards understanding why vertex cover can be solved so efficiently in practice. But actually, we can learn even more from our analysis. And for that, let's take a look at a slightly different problem, which is vertex cover approximation. Here, the goal is not to find the absolute smallest set of vertices that covers all edges. Instead, we aim for a solution that is reasonably small, and we hope that this slightly easier problem allows us to find solutions more quickly. A simple way to approximate vertex cover is with a greedy algorithm. At each step, we just pick the vertex that covers the most edges and greedily add it to the solution. In this example, we would start with the node at the top. Once added to our vertex cover, all its incident edges are taken care of, and it suffices to treat the rest of the graph as if they were removed. And now we simply repeat this process, always picking the vertex with the largest degree, so the one covering most edges, and adding it to our cover. We keep going until all edges are covered. The hope then is that we end up with a cover that is not much larger than an optimal one. But how far off will we be? Well, this is typically measured with the approximation factor, telling us by how much the size of the optimal solution needs to be multiplied to get to the solution size of our approximation. For example, it was shown that the greedy algorithm we have just seen has an approximation factor of log n, meaning the approximate solution may be off by a factor of at least the logarithm of the number of vertices in the graph. Interestingly, there is another approximation algorithm that guarantees a factor 2 approximation. The best known polynomial time approximation reduces this to 2 minus 1 over the square root of log n. And there's reason to believe that it is NP hard to obtain 2 minus some positive constant. And we for sure know that it is NP hard to obtain a square root 2 approximation. However, as before, there's quite a difference between our theoretical understanding of the problem and what actually happens in practice. While the greedy algorithm we just discussed has a logarithmic approximation factor in the worst case, it was observed to perform incredibly well on several real-world networks. And here you can see the results of our reproduction of these previous observations. For every network tested, the greedy algorithm produced vertex covers with approximation ratios very close to the optimal value of 1. Even for the worst example on the right, the approximate solution is only 5% larger than the optimum. And as you can probably guess by now, we investigated this discrepancy between theory and practice through the lens of hyperbolic geometry. So let's have a look at how the greedy algorithm behaves on hyperbolic random graphs. Recall that vertices not too close to the boundary of the graph are likely to dominate and can be added to the cover safely. And we have also seen that this inner region is where the high degree vertices live. So from this we can already tell that the greedy algorithm prefers vertices that can be added safely and is therefore on track towards getting an optimal solution. But once all these safe vertices are added and removed, the remaining vertices all have roughly the same degree. At that point, choosing based on degree becomes almost random, which doesn't seem very clever. And this led to an exciting discovery. While we set out to understand why the greedy algorithm works so well in practice, and had just gotten some insights towards that, our analysis now tells us that the algorithm may even be giving away quite a bit when it comes to the low degree vertices. Surely there must be room for improvement there. So then our new goal was to design an even better algorithm, one that improves over the greedy without sacrificing too much running time. And for the rest of the video, I'll walk you through what we came up with and how it outperforms the greedy algorithm we've discussed so far. We began by taking over the good parts of the greedy one, namely starting with the high degree vertices. However, making use of the underlying geometry, we picked the vertices by increasing radius, so by increasing distance to the center. As we've seen before, we find the high degree vertices in the center and the low degree ones near the boundary. So this is close to picking the vertices greedily by decreasing degree. Each vertex that we find, we add greedily to our approximate solution. Then we find all its neighbors and remove the edges to them, since they are covered by the blue vertex anyways. Now this is where the crucial adjustment comes in. We check which neighbors have been separated from the rest of the graph in the process, and whenever we find a very small graph that got separated that way, we just compute an optimal solution for this tiny part. These separated and solved components are shown in yellow. Then we just continue with the next best vertex closest to the center and repeat the process. Add it to the cover, remove the edges to its neighbors and solve small separated components exactly. Now if we repeat this process until all parts of the graph are either taken greedily or solved exactly, we end up with a picture like this. And this is really nice because we can see that, as before, we greedily added all the vertices near the center that can be added safely anyways, but where the greedy algorithm basically picked vertices at random, we compute optimal solutions instead. So overall, we should end up with very good approximation rates. And as it turns out, we do. Our analysis shows that our algorithm computes an approximate vertex cover of a hyperbolic random graph in quasi-linear time, and such that the approximation ratio is approaching the optimum at 1 with increasing graph size. So we have a fast algorithm that is very likely to yield a solution whose size is close to the best possible. And at least conceptually, it is somewhat straightforward to see why the approximation quality is so good. Basically, our proof consists of 3 steps. First, we make use of the fact that the size of an optimal solution is linear in the number of vertices in the networks we are studying. So we only have to show that the number of vertices we greedily add on top is sublinear, and we aim to do that in 2 steps. For one, we want to show that there exists a threshold radius such that only sublinearly many vertices are contained inside, and such that removing them decomposes the graph into mostly small components. And then we show that there are only sublinearly many vertices in components that were not small enough to be solved exactly. Note that we overestimate the number of vertices in our approximate solution with this last step. This helps us in making the analysis easier. We assume that the algorithm would greedily pick all the vertices in these non-small components, while actually it would just pick a few until also the non-small components get separated into small ones. However, this will suffice for our purposes. So let's take a closer look. We consider the vertices within the blue region to be added to the cover greedily, which means they are also removed from the graph. And we want to show that only few vertices are contained in the remaining separated components exceeding a given size. To bound the number of those, we discretized the disk containing all vertices into thin sectors in such a way that components cannot span empty sectors. Specifically, the width of the sectors is chosen such that even the vertex with the largest possible neighborhood cannot connect to anything that is more than one sector away. Now, components that contain only few nodes are just solved exactly, and we're not interested in those. Instead, we are interested in larger components, and essentially a component can be too large for two reasons. On the one hand, even though it spans only few sectors, it may still contain many vertices. On the other hand, even if the sectors themselves are not packed too much, a component may still be large if it spans many of such sectors. So for things to work out for us, we need that the sectors contain only few vertices. In fact, it would be good if we found many empty ones, so that we get many small components. This essentially means that the whole analysis boils down to understanding how many vertices fall into a sector, and this is something that we can just compute. The first step is determining the expected number of vertices in a sector. The formula itself is not particularly relevant at this point, but the limits of the integrals are. In the outer integral, we consider the radii between which the vertices of interest lie. We start at the blue threshold radius, inside of which we consider everything removed. And we end at the boundary of the disk containing all the vertices of our hyperbolic random graph. The inner integral considers the angular width of the sector. Now the radius of the disk is defined by the model, but the blue radius and the red angle are for us to determine. Unfortunately, they don't play along nicely. Let me explain. We want the blue radius to be as small as possible, since it represents the portion of the graph we pick greedily. The smaller the radius, the fewer greedy additions to our cover, and in the end we need our cover to contain as few vertices as possible. However, decreasing the radius forces us to increase the angle phi. And this is bad for us, since the larger phi, the easier it is for the sector to contain many vertices, and we actually would like to have many sectors to be empty, which means we need phi to be small. Now you may wonder, why are the radius and the angle tied together in that way? Well, recall that phi was chosen such that a vertex with the largest possible neighborhood cannot connect beyond an empty sector. If we decrease the radius, we allow for vertices closer towards the center, and we have already seen that they have larger neighborhood regions. So to maintain that such a vertex cannot connect beyond an empty sector, we have to increase the angular width of these sectors. As you can see, there is an unfortunate interplay, as we'd like both radius and angle to be small, but decreasing one increases the other. However, when juggling the math a bit, we found that there is just the right sweet spot at which everything falls into place. Not too many vertices are contained in the blue region in the middle. Sufficiently many sectors are empty such that we get mostly small components that are solved exactly, and also the remaining non-small components contain sufficiently few vertices. And with that, we were able to prove that our fast approximation algorithm does indeed yield solutions that are only slightly larger than optimal solutions. Well, at least in theory. But how does it perform in practice? To test our improved algorithm, we ran it on the same networks as the original greedy algorithm, whose near-optimal results you can see here. But how does our improved algorithm compare? Well, it decreases the approximation ratios quite a bit, bringing them even closer to 1. In fact, on 4 networks, it even found an optimal solution, whereas the original greedy algorithm did not. And on more than 2/3 of the networks, our algorithm cut the error to less than half of that of the original greedy algorithm. To wrap up, we have seen how real-world networks are modeled using hyperbolic geometry. Over the course of my PhD, we have devised 4 analyses showing how this connection between graphs and geometry can be used to understand why algorithms perform better in practice than one would expect when looking at the worst-case performance that is often focused on in theory. And as we've just seen, these insights can go beyond explanations, uncovering weaknesses in current methods and inspiring the design of even better algorithms. I hope this video has given you a glimpse of the beauty and utility of hyperbolic geometry in network science. Thank you for watching.